Hi, welcome to session 11, collaboration. My name is Francisco Ortega from Colorado State University. It's a pleasure to be here. I think it's going to be a great session. We have 5 papers. Um, and uh, and anyways, if there's any questions, make sure to go to Slido, that's sli.do, hashtag IEEE 2020, look for session 11 and post your questions. And remember, you can watch this via Twitch or Mozilla Hubs. The first paper is augmented virtual teleportation for high fidelity telecollaboration, and the sir, and Daniel Medeiros is presenting this paper. Thank you.
I'm Tianhui, call me TJ. We also have Stephen, Daniel. They're from Computational Media Innovation Center, Victoria University of Wellington. We are presenting our paper in New Zealand. Our local time will be at 7 a.m. when presented. With thanks to all the online audiences and organizing committee of IEEE for this online presentation opportunity. This is one of the situations. To fix the problem on site, collaborators need to be in the same space with clear situational awareness of the worksite, communicate face-to-face, share information mutually, work together in live to solve the problem. The current video conferencing system has limitation to meet the requirement. Therefore, the people need travel. A long-hour flight costs travel time and money, produces carbon emission, may cause climate change. Also, it can cause health and safety issues. Human teleportation can be one of the solutions, but is still in the movie and fiction. It could be convenient to travel, but it can cause significant health and safety issues. We present augmented virtual teleportation, simply AVT, or remote workspace collaboration. Remote traveler will stay in their physical space, but will have full situational awareness in the worksite through live streaming 360 video shown in VR. Local host in AR will communicate face-to-face with 3D avatar of remote traveler overlaid into 360 camera. Collaborators work together in a high fidelity mixed reality collaboration space in live. VR-based collaboration provides a high sense of presence but limited in the virtual space. AR-based method is good to share information, but collaborators stay in their own space with limited situational awareness in the remote worksite. A symmetric setup that converges VR and AR can solve the limitation. The recent work based on the 3D point cloud provides a good solution that has limitation in situational awareness of surroundings and fidelity in live collaboration. 360 video-based method is promising to provide high situational awareness and visual fidelity in live. The recent wearable setup is good to share the view, but has limitation in face-to-face communication. As we are aware, AVT is the first unified system that assembles all the necessary components in one robust and also cost-effective framework to meet the needs for high-fidelity telecollaboration. Work together in live at a high-fidelity MR workspace while communicating face-to-face with remote situational awareness. I'll pass it over to Stephen for the detail.
Thanks, TJ. So as already presented, the system uses a 360-degree camera to teleport remote users to a different space. Once there, the users can interact with virtual objects augmented by the system into the real-world environment. Users can also use rays projecting from their controllers to clarify communication when pointing at objects. The space containing the users and virtual elements is called the Mixed Reality Collaboration Space, or more simply, the MRC space. Because the VR traveler requires the 360 video, camera to view the MRC space, we stream the 360 video directly to the VR Traveler to ensure the lowest possible latency. Both users also use the 360 video to provide believable lighting and composition of virtual objects into the real world. The 360 video and MRC space is synced between the two users before rendering to their respective headsets. The VR Traveler uses a VR headset, as seen in the top figure, to view the MRC space and can view the space through a live streamed 360 video. This gives the VR Traveler full rotational freedom to view the MRC space. The AR host uses an AR head-mounted display to view the MRC space. We attach a Z-Mini camera to a headset to create a see-through head-mounted display. Through the headset, the AR host can see an avatar representation of the VR Traveler, as seen in the bottom figure. The pose of the avatar is driven by the position and orientation of the VR Traveler's headset and controllers. Inverse kinematics is used to calculate the arm poses. So once both users are in the system, their spaces should be aligned so that the virtual objects appear at the correct location in space. This is done manually by matching the location of the VR Traveler with the 360 camera. Real-world geometry scanned by the AR host is synced with the VR Traveler. We also project the 360 video onto the geometry as when viewed by the VR Traveler to give a sense of depth. Once aligned, users can start to use the system. The AR host computer is used to store the true state of the system with the virtual objects locations and how the physics are simulated. However, objects will be simulated on the VR Traveler's computer whenever the VR Traveler interacts with those objects to ensure a smooth interaction. We have also included two interface systems to handle different aspects of the system. The collaboration is done using the shared window system, as seen in the top figure, which can be viewed and interacted by anyone. Personal settings for each user can be accessed through their own personal menu, which only they can view and interact with. Objects are composited into the real world by taking account of real world lighting. We render a virtual representation of the scene using planes representing the floor, walls, and ceiling to catch shadows. And the 360 video is also used to provide ambient high frequency lighting and ambient lighting. The same setup is used for both the AR and VR views to provide similar levels of visual quality for both users. Our system runs at a frame rate of 90 Hz, which is the optimal frame rate for most VR headsets. We also tested 360 cameras and chose to use the Insta360 Pro 2, which provided 1.2 seconds of latency when viewed by the VR Traveler. In this video, we are demonstrating the system in use after the system has already been calibrated. Here, the VR Traveler has connected to the MRC space, where the AR host is co-located with the 360 camera. The users in this video are able to use the spatial awareness provided through the 360 camera and the AR headset and face-to-face interactions to collaborate on an interior design task. Other applications that can benefit from the face-to-face interactions and spatial awareness of the AVT system include, such as in this case, remotely assisting and guiding people to perform tasks, training people to perform tasks or to use equipment by rendering virtual replicas of that equipment in the MRC space, and remotely presenting to people. These applications all benefit from the sense of co-presence and spatial presence. I'll now pass over to Daniel to discuss how we evaluated the system for presence.
Hello, everybody. So due to the asymmetric nature of the system, both VR Traveler and our host conditions, we need to ensure like equivalent levels of presence between them. In AVT, the VR Traveler is not physically at the collaboration space, and therefore the presence could be limited by the fidelity of the remote MRC space. but co-presence might be higher than the AR host, since VR traveler see a real person in the 360 video. The AR host is physically at the collaboration space, and therefore the presence will be surely high, but co-presence might be limited due to the abstract avatar of the VR traveler. So even though this difference, we still argue that our system guarantees that both users who both present and co-presence with a high level of both senses and this asymmetric space. So to ensure that, we designed a user study in order to make sure that both VR travelers and AR hosts have equivalent high levels of social and spatial presence. To evaluate our system, we performed this user study with 40 participants with ages varied from 20 to 35 years, and most of them did not have experience with AR or VR setups. We used 3 different metrics to evaluate our system, which include social presence, which measures how people feel together in the same environment. And in this measure, we chose 3 of their submeasures: co-presence, with the feeling of being co-located in the same space; attention allocation, which is the amount of attention one gives to the other; and perceived message understanding, which measures how people understand the message being given. The spatial presence deal with how people feel to be especially present in a location. It is related to the concept of being there, also known as presence. For us to use a study, we focus on 2 dimensions of spatial presence, which is the sense of location, which is the feeling of being physically located in the same environment, and spatial situational model, which relates to how people process spatial cues and interpret them related to the space. We also included an additional 7 Likert scale questionnaires to include aspects not covered by the above 2 questionnaires. These questions included aspects such as task easiness, communication, and collaboration. The study was conducted in uncontrolled environments in 2 physical separated rooms, and we first introduced the objectives, then the users did a pre-test questionnaire, they did the training scenario, then performed the main task, then answered the post-test questionnaire, and finally conducted a semi-structured interview according to collect their subjective opinions. So in the training tasks, users were asked to freely place objects in the MRC space. In this task, they could select between different objects to furnish the MRC space in order to get acquainted with the system for a maximum period of 20 minutes. In the main task, one user was asked to place shapes in the environment and was guided by the other who had a blueprint where the objects should be placed. This blueprint was generated randomly and indicated where the object should be placed. And after its completion, the roles were switched. So to test for statistical significance, we used the Mann-Whitney test for between groups comparisons between the AR and VR users. Then we used the additional 2 one-sided parity tests, also called TOS test, to test for equivalence between the 2 groups. Regarding social presence, we found no statistical significance in the co-presence measure, and SIMBO were statistically equivalent in all subscales and were high in the subscales, including co-presence, attention allocation, and perceived message understanding. This was also noticed in spatial presence in both self-location and spatial situational model, where both had a high level of these measures. The results of the questionnaires show us that both users found it easy to understand, people using pointing cues, communicate using voice, creating, selecting, and moving objects around in both tasks, and collaborate with the partners in both setups. We also can showcase some limitations in our system. The first of them is latency, which is still high for remote telepresence, which is 1.2 seconds, but we can say people still consider it an enjoyable experience, and they can really feel they were there together in the same room and were able to collaborate with the partner. So we hope that future technology will improve on this by balancing both latency and visual quality. The avatar representation of the VR traveler is an abstract outline of a person, which may limit more expressive scenarios that require richer body language, but we will include more richer avatars in future iterations. Our setup is based on a static 360 camera capturing monoscopic 360 video, and which may still be limiting for some scenarios where people need to move around. However, the current hardware technology still do not provide fully walkable high-fidelity 360 live scenes. So in conclusion, we presented the first unified and cost-effective system which meets requirements for remote workspace collaboration, remote situation awareness, face-to-face mutual live collaboration, and a high-fidelity MRC space, which converges AR and VR to enable efficient remote collaboration in a high-fidelity space by ensuring high level of social and spatial presence for both users. With AVT, why do you need an airport when you can teleport? So with that, I conclude my talk, and I thank you everybody that's listening from all over the world. Thank you.
Yes. Well, that was a great presentation. Thank you, Daniel. There's quite a few questions. We may not be able to go through all of them. I will send the questions at the end of the session to the authors, and they may want to post them in Slack if possible. But let me start. One of the questions is, how can the t-test be used to confirm non-difference between conditions? I thought that the null hypothesis can never be accepted but only rejected.
Can you repeat the question, please?
How can the t-test be used to confirm non-differences between conditions? I thought that the null hypothesis can never be accepted but only rejected. So I'm not sure what the question the person was trying to get here.
Yeah, we didn't use t-test for this test. Basically, we wanted equivalence between the two sets of data. So that's the idea that we had to do. Basically, we did a bit kind of between groups statistical test first to ensure that all of the questions were not statistically significant. So after that, we used the two one-sided t-test, which is basically used to test for equivalence between the two sets of data. And only there we could verify our hypothesis.
Right. Tobias Hollerer asks the following question. The 360 footage is mono, right? Can you comment on artifacts disruption from the stereo/non-stereo mismatch between background video and VR content?
Yes, I'll comment on that. So we use rough geometry reconstruction of the scene, and we project the 360 video onto that geometry. So this is for the VR Traveler. So that you'll still get some artifacts. For example, if people will walk, if people say walk in front of virtual objects, that will appear behind them. So that will be more future work we can address. But yeah, for now, the rough geometry is good enough to at least make objects feel grounded on the, say, on the floor.
Thank you for that. I'll have time for one more quick question. So someone asked, when you have a 1.2 second latency, how does the interaction of the objects work having this long delay? So we know that even 20 millisecond delay can be problematic, and for sure anything above 50 milliseconds. Can you expand on this? How was the interaction when people were moving the objects on this work? I think that's what the person means.
Yep, so 1.2 seconds, that is only for the 360 video itself. Everything else is much lower.
What was the latency?
We haven't actually tested the latency for the rest. I think it was, if I had to take a guess, I don't know, sort of probably more 50 milliseconds at max, really, I'd reckon. But that's more just a pure guess rather than an actual reading. But on top of that, when it comes to object manipulation, we actually simulate that on the machine of whoever is doing the manipulation. So for example, everything has been simulated on the AR host normally, but then once the VR traveler starts to interact with an object, then we will switch over the physics to being simulated on the VR traveler just to make it easier to manipulate.
Yeah, this is a great answer. I know that you guys want to say more, but thank you for, we have to move to the next paper. Thank you so much for presenting this paper. And we're going to move to the next paper, which is going to be presented by, we're not used to being on this online platform for a conference. Gan-San Lee is going to present the next paper, which is a user study on view sharing techniques for one-to-many mixed reality collaborators. Are you ready?
Hello, everyone. I'm Gan-San Lee from Korea University, and I'll be presenting our work, a user study on view sharing techniques for one-to-many mixed reality collaborations. So the area of mixed reality collaboration is gaining interest with the development of virtual reality and augmented reality technologies. While previous works mostly focused on one-to-one collaborations, practical uses of MR collaboration includes one-to-many collaborations. View sharing techniques of multiple users should be taken into consideration for real-world scenarios. To this end, we created an MR collaboration scenario where one VR remote expert instructs multiple AR local users. Our work focuses on comparing with which view sharing technique is the most effective in the remote expert's perspective. In our study, the VR remote expert is wearing an HTC Vive HMD, and the AR local users are wearing Microsoft HoloLens with a 360 camera mounted on top. In our scenario, the remote expert instructs two local users to perform a task. The task is to direct the local user's actions to search for TANs and assemble them to a certain target configuration. For the workspace setup, a room is separated with a partition in the middle, and one side being the VR remote expert space, which is the left picture on the figure above, and the other side is the AR local user space, which is, of course, the picture on the right. In the local user space, there are search tables and an assembly table. The search table consists of 6 tables surrounding the local users where TANs are scattered all around, whereas the assembly table is a separate table in the middle for assembling the TANs. In our work, we compared 3 common view sharing techniques that are used in one-to-one MR collaborations. We modified them to fit our one-to-many collaboration scenario. The 3 techniques are named 2D video, 360 video, and 3D model. So let's take a look at them one by one. The first technique is 2D video. In this technique, the live video stream from the local user's HoloLens camera is shared with the expert, and the video frame is fixed to the VR HMD screen. To distinguish between the user's views, the outline of the video frame is color-coded. Distinct features are switching between the 2 local users' views with a fade-in, fade-out effect to minimize the remote expert's sickness during transition, and share remote expert's line pointer with local users. The second technique, 360 video, utilizes the 360 camera mounted on the local user's HoloLens. Here, the live panorama video stream captured from the local user's 360 camera is shared with the expert. We implemented counter rotation to make sure the remote expert's view is independent of the local user's view. The view direction of the local user is depicted with a color-coded video frame. The technique provides the remote expert with features as following. The transition effects and pointer sharing is also implemented as done in 2D video. And additionally, the remote expert can view the local user's workspace independently of the local user's viewing direction. Last but not least is the 3D model technique. This technique pre-reconstructs the local user's workspace and displays a live video billboard attached to the front of the user's avatar. It goes without saying that all avatars' movements are synchronized with the local users. The 3D model enables the remote expert to freely walk through the reconstructed space in VR, and the remote expert's position and pointing line are simultaneously shared to both local users in this case. With the 3 view sharing techniques, we first conducted a pilot test to identify the weaknesses of each view sharing techniques and improve them. In this pilot test, 2 actors were employed as local users to minimize performance differences, and 8 volunteers were recruited as the remote expert. Participants freely instructed between local users to search and assemble TANs with the 3 view sharing techniques. Collecting the feedback for each technique, we were able to modify and improve each of them. After trying out 2D video, there were comments as the view being full screen is unnecessarily big and it is hard to perceive it at a glance. We thus disabled the full screen mode, which resulted in the video having a black background as the picture shown below. Next, in 360 video, participants complained that the image distortion created by the panoramic video makes it quite hard to identify TANs that are relatively far away. To address that issue, we added the zoom in, zoom out function, and the zoom in part is shown as the figure below. There are also some feedback with the 3D model technique. As the current implementation uses a billboard, participants pointed out that the live video is only visible from a certain angle, which is especially inconvenient when instructing multiple users. A function is added so that the remote expert can switch between video billboard and a video projector. The latter is implemented with projected texture mapping. Furthermore, some participants stated that the pre-reconstructed 3D scene does not show the change made in the real-world workspace. Additional implementation enabled users to freeze the video frame in order to save the changes they have made to the static virtual workspace. Now, in the main experiment, we wanted to identify which of the view sharing techniques is the best for the remote expert in a one-to-many MR collaboration scenario. 17 subjects participated as the remote expert, and this time a target configuration is rendered in the subject's VR screen. The goal of the task is to instruct the local users either verbally or with line pointing, and correctly search and assemble TANs. Subjects were given a training session before trying out each view sharing technique. Seen below is an example of a target configuration that the subject is aiming for and the initial placement of TANs that the subject should replace or add TANs to. We assume 2 common collaboration scenarios in the real world for our main experiment. Scenario 1, independent tasks, has each local user involved in both search and assemble procedures. Each local user can only access to 3 search tables, which is either the right or the left side of the room, that are assigned to him or her, while they both can use the assembly table, which is in the middle. As for scenario 2, divided tasks, each local user is dedicated to a certain role, either search or assembly. The user in charge of search can access to all 6 search tables, whereas the one in charge of assembly is fixed to the assembly table. Now, with this in mind, let me present the results of the experiment. First, we analyzed the objective performance measures, search and assembly times for each scenario. For search time, 3D model was significantly shorter for both scenario 1 and 2. This can be explained by the high DOF of 3D model, allowing experts freedom of movement. For assembly time, 2D video was the shortest in scenario 1, since the remote expert's fixed view helped subjects to focus on the assembly procedure itself. However, in scenario 2, there were no significant differences observed between the techniques. Participants explained that this is because the local user's camera remained largely still during the assembly procedure, which gave little differences in experiencing each view sharing techniques. We also conducted how often subjects switch between the 2 local users in instructing them. In scenario 1, 2D video had the highest user switching count, while 3D model had the lowest. We observed that subjects often failed to find a specific tan using 2D video because of its small field of view. Some of the participants stated that 2D video and 360 video, they needed a second to realize where and what the local users were performing. There are no significant differences in scenario 2, since the local users clearly had different roles. Next, we analyzed the subjective performance measure by usability, workload, and social presence. So 3D model showed the best results in both scenarios for both usability and workload. Subjects stated, despite the additional training needed for 3D model, that technique was especially useful while performing the task. The social presence score was also the highest in 3D model. This is because subjects were able to feel like they were working together with the local users at the same place with little restriction. The results of the objective and subjective measure of performance explain subjects' preference toward each technique. Subjects' preference ranking showed that 3D model was the most preferred technique for both scenarios, while 2D video was the least preferred one. To summarize, 3D model was time efficient, usable, less demanding, and the most preferred in one-to-many MR collaborations. Finally, we would also like to talk about the practicality of the additional features we implemented for 360 video and 3D model. While the zoom in count for 360 video did not show much difference between scenarios, for 3D model, the use of video projector mode and freeze feature was lower for scenario 2 than scenario 1. Since one local user had a fixed position, the motivation to use the projector decreased. The decreased use of freeze feature was also derived from a similar reason. The user performing the assembly procedure staying largely still. A few subjects stated that the freeze feature might be more suitable for complex applications where it is hard to remember all the changes they have made. Finally, let me conclude and summarize the presentation. We presented and evaluated 3 view sharing techniques for one-to-many MR collaborations: 2D video, 360 video, and 3D model. We compared these techniques in 2 collaborative tasks, and the overall results indicated that 3D model was the most preferred technique with the best performance. As for our future work, we envision to further research view sharing techniques with different multimodal interactions, such as different visual cues or even haptic cues, and also scenarios where local users and remote expert are allowed to freely converse. As the experience of local users was actually neglected in the current study, we would also like to investigate the experience and interaction between co-located local users for each technique. Thank you so much for your attention.
Thank you so much for your presentation, Ganson Lee. So we're gonna do a virtual, we should get that sound effect. So thank you so much. It was a very good presentation. I wanna remind the audience to go to Slido, sli.do, IEEE VR 2020 hashtag, to ask questions about this or the following presentations. Also remember to go to Mozilla Hubs whenever you have a break, and there's a lot of stuff going on. So please check the Mozilla Hubs as well. Let's see some of the questions. So while the questions are coming in, I do want to ask you one question. You were saying that there was no significant difference between the scenarios in the zooming and video 360 in one of your previous slides. Was kind of like almost one of the last slides that you presented. You were saying there was no significant difference, correct?
No significant differences on what technique? Sorry, I missed that part.
I think what I wrote was zooming and video 360, I think.
360 video. Are you talking about the zooming count?
Yeah, that was the slide that you had towards the end. I think it's almost the last slide that you had on the PowerPoint. There was no significant difference between those two techniques. And what I wanted to ask you is, what do you conclude from that finding, that there's no significant difference?
No significant difference between the 360 video in zooming counts. Am I getting that correctly?
I think so. I don't remember the slide anymore. I wrote it down.
If you're talking about the zooming count and no significant difference between two scenarios, it's most likely because the searching procedure itself didn't really have much differences in scenario 1 and 2, since the kind of distortion caused by the panoramic video still remains.
Right.
And that is the main reason that there were no significant differences between those scenarios.
Yeah, thank you. Yeah, I tend to be a little more conservative with that in terms of there's no significant difference. Yeah, it is possible that may be it, but it's just not, you know, you may run the experiment again with older population and it may be different, right? So that's where I try to be a little careful with the no significant difference, but I understand. I think it was a very nice presentation. I did get a question from the audience. It says, were the same two actors employed in both the pilot and the main experiment? And if not, was the effect of learning on the first few trials of the main experiment? So were the two actors,
So the actors were actually the same for the pilot test and the experiments. And of course, that doesn't exactly affect the experience of the remote expert, which is the participants. And we were just trying to assure that our results wasn't affected by the performance of the local users. So just to ensure that there's no actual performance gap, that is the actual reason that we employed local users as actors, and we actually used the same people throughout the whole experiment.
Thank you. Yeah, and actually it makes sense, right? That's your control variable. You wanna have the actors, you know, you're not testing the actors. Thank you for that. This last question I'm gonna ask, this is coming from the audience, did you observe forms of mixed reality collaborations that were especially enabled by mixed reality? Did users behave in ways different from real life collaboration?
Oh, so while conducting this experiment, we definitely saw some differences in real world and this virtual kind of mixed reality collaborations with 2D video and 360 video, while there were not really much differences in doing 3D model because they can actually see all the local users and remote expert on the same space and actually see how they process with the task. So I just want to say that there were least differences between the real world and the mixed reality when doing the last technique.
Well, Gansan Ali, I want to thank you so much for your presentation, for being here under these circumstances right now, and thank you so much for everything. Our next presenter, um, paper's title is Optimization and Manipulation of Contextual Mutual Spaces for Multi-User Virtual and Augmented Reality Interaction, presented by Mohammed Kesavarsi. I apologize for mispronouncing the name. And I want to remind the audience to go to Slido, SLI.do, to ask any questions about these papers. And remember our Mozilla Hubs. There's a lot of stuff going on in Mozilla Hubs. Thank you.
Hello, everyone. My name is Mohammed Keshavarzi. I'm a PhD student at the University of California, Berkeley. I'm so glad to have the opportunity to talk about our research on optimizing and manipulating mutual spaces in spatial computing interactions. So here we are in 2020, in the middle of an unfortunate pandemic crisis. The streets and highways of our busiest cities have become empty, as many of the countries are trying to contain the outbreak, while our indoor lives are fading away. A lot of us are trying to keep up with our everyday business by working from home and running remote meetings, classes, and conferences, and basically trying to communicate with our colleagues and friends and peers and loved ones. But I'm sure we all know and feel how different it is or was to come together and gather in the same room rather than meeting everyone through a flat screen. So what is it of these in-person meetings that we're missing in our virtual 2D video conferencing? Let's just take a deeper look at this picture, for instance. You see, the enthusiasm, the facial expressions, the body gestures, these can all be captured by high quality cameras currently available in our video conferencing systems. But what may be missing is that all these fine qualities are encapsulated within a certain space owned by someone. We use it to express ourselves, like this little girl who is rising up to say something while also expanding her spatial ground. And in the end, we bring our individual spaces together and share it. You know, space matters. It also plays an important role in our professional meeting for important decision-making and negotiations, like this picture where a team scrambled around a table, sharing a mutual space while maintaining their own individual part of it. And you see, by leaning forward and showing a strong body language, this man is using his space effectively, as if he wants to take a little more control of the social dynamics of the moment. So yes, mutual space matters, and mutual space is actually one of those critical qualities we cannot capture in current 2D video conferencing. And that brings us to the importance of exploring and utilizing spatial computing interfaces like augmented and virtual reality, which can theoretically maintain these mutual qualities in collaborative settings. This work, called Holoportation, developed at Microsoft Research, is one of the many great examples of how mutual space can be preserved in an augmented reality setting. Look how the presenter here, Shahram Izadi, steps back from his ground to allow his daughter to move around the table. I was personally very inspired by this work the day I saw it back in 2016. And it illustrated a very bright future on how telepresence systems can be utilized for remote communications. But if we just pause the video for a second, we do see some critical issues. First off, the amount of open space allocated for this experience in both rooms is pretty large. And if we take a closer look, we see some markers on the floor indicating that objects of these rooms, the chair and the table, were manually calibrated beforehand. But those settings may not be really feasible in our everyday spaces. To have large and accessible open spaces without any obstacles, and each time manually calibrating your surrounding furniture with each telepresent participant without knowing how the other spaces of those participants even look like. So it's fair to say, with our current real-world environments and surroundings, collaborative spatial computing has spatial limitations itself. So let me open this up a little more. Say we have 3 individuals wanting to hold a remote telepresence call with each other. User A in red, user B in yellow, and user C in blue. User A resides in this very large living room. You can see a perspective view on the left and a floor plan view on the right. User B, however, wants to join the telepresence from her small office. And user C is working from home and is planning to meet in his bedroom space, which has a little open area for the others to join. So let's look at the first problematic scenario where spatial collision occurs when participants show up in each other's spaces. Let's see how. Okay, this is user's A room, and he's hosting the meeting, which augments virtual avatars of users B and user C in an open area of his pretty big living room. With holding the same positional relationships with each other. In users B's space, however, she actually sees no one, basically no one. But if you look at the floor plan view on the right, the other 2 gentlemen are located outside her office. You see, when keeping the same positional relationships with each other, initiated in the previous scene, they just don't fit in user B's office. And a more weird thing happens in user C's room, when user A is looking like a ghost stuck in the wall and dresser, while user B is also colliding with the furniture. Both remote individuals are in undesirable locations. Now you may ask, why do you need to keep the positional relationship constant? Why can't each user have the option to force position and manually identify a desirable location for remote avatars to be augmented in its space? So let's see what happens. Here we have the participants holding constant positional relationship with each other in all rooms. Now, let's just allow them to manually force position remote avatars in their own preference. So here's the problem. When user A is looking and talking with user C in his own room shown on the left, in user's B room, shown in the middle, the direction user A is facing is not quite right. Instead of looking at user C, it looks like user A is talking to the wall, and the line of sight is incorrect. This becomes much more abnormal in user C's location on the right, where user A is supposed to be facing at user C, but instead is looking at user B in a complete other direction. So how do we address this challenge? And this is where our contribution kicks in. Our first goal is to locate where users can walk and talk in their own room without colliding with objects in the other remote rooms. We do this by finding the mutual space between all rooms. Let's see how that works. Say we have 4 rooms with 4 individuals planning to remotely meet each other in a spatial computing settings. First, we perform semantic segmentation to determine the bounding box of each object in the room. Next, we intend to locate the standable spaces. Standable spaces are basically the volume of the room in which no object located within a human height is present. And the user movement can be performed freely without a risk of colliding an object in its surrounding physical environment. We calculate the standable space by simply subtracting the area of the object of which the object occupies in a room from the room itself. We do this with all rooms. Next, we define a rigid body function here called G, where theta describes a transformation vector. We then run a genetic optimization to determine the optimal theta of each rigid body motion so that the area of the overlap between the boundaries become maximum. Now, if we map the mutual space back to the room, shown here in a blue area, when all users stand and walk within the blue area of their own space, they are guaranteed not to cause virtual conflicts or line of sight mismatches within each other's spaces. Now, to add a little more flexibility and increase mutual usable spaces, we also define sittable spaces. Sittable spaces normally extend the standable spaces by adding areas where humans are able to sit on, such as sofas, chairs, and bed. Again, if we if we go through the same process, this time with sittable spaces, we observe larger mutual spaces, which users can stand, sit, and walk and move around those spaces without worrying to cause any unwanted collisions in remote rooms. Okay, so we wanted to implement our proposed framework on some real-world data sets just to see how it works. We chose a Matterport 3D data set for this, which includes a wide variety of residential houses with diverse styles and room functions. As you see here, the standable areas are indicated in green and the non-standable spaces are colored in red. And here on the right, the sittable spaces are visualized in yellow. Again, green showing the standable space and red will be the non-standable space. Moving on to identifying the mutual space between multiple rooms, this illustration shows how our genetic algorithm is gradually improving the results and expanding the mutual area in higher generation values. And here we show the mutual ground in blue after 40 generations of the search between these rooms. But then the question arises, what if we need more mutual space? What if it's just not enough and the identified mutual grounds are small, too small for the remote communication purpose? Say you want to play a game or inspect an object between participants where the object doesn't fit the mutual boundary. What do we do? So that brings us to our second goal, which is rearranging the furniture so that we increase the mutual space while minimizing the overall effort to do so. So the effort of each move is basically calculated by multiplying the distance of the object's translation by the object's width. So in simple terms, moving a bed is considered to have a higher effort value than moving the chair for the same distance. So again, our goal is to slightly manipulate the room layout to increase mutual space with minimum effort. To simplify this process for the user, we define increased steps, where each step has the goal to achieve 10% additional mutual space from its previous step, while maintaining the effort to do so, while maintaining the minimum effort to do so. Now, let's take a look at how the furniture manipulation system works in an example. Again, we use real-world data sets from the Matterport 3D scenes for this experiment. We have a family room, an office, and a bedroom. First, we extract the standable and non-standable spaces using the methods previously explained. Next, by utilizing our proposed mutual space identification system, we can locate the maximum mutual ground between these three rooms. We then use a strength Pareto evolutionary solver to run the optimization for the two objectives: effort, which is shown on the vertical axis, and the mutual area, which is on the horizontal axis, which we want to increase. So when we plot the rearrangement solution space, we can find the initial arrangement point on the Pareto frontier with the e-value of 0. Then, by increasing the area in each step, we find the rearrangement solution which satisfies the increased area goal and holds the lowest effort value in that step. And as you see, after 5 steps, we significantly increase the mutual space between the rooms while minimizing the effort required for the furniture rearrangement. Finally, to have a better understanding on how users would experience the system's output, we deploy our proposed method on a Microsoft HoloLens as an augmented reality visualization. For the target spaces, we scanned our office area at Berkeley and chose a conference room, a kitchen, and our main laboratory space for our experiment. We also provided the bounding boxes and semantic labelings for the model. The system then calculated the standable and open spaces, visualized here in green, and the mutual spaces seen here in blue. Here you see the view of the HoloLens in the kitchen. We visualize the mutual space boundary with an offset of 47 centimeters of the ground so the users can clearly relate to it. And here you see the main laboratory itself. Again, the blue areas indicate that you can freely move around in this boundary without causing any conflicts in other rooms. Finally, a floor plan view of the space with different screenshots taken in different locations from the HoloLens headset. So, limitations. Of course, there is limitations to our work. First off, in our current version, the crescent steps may not have any continuous relationships with each other. For example, in step 1, you might be moving a chair in a certain direction to achieve minimum effort. But if you then decide to move to step 2, it doesn't take into account step 1's transformation. The next limitation is that our system doesn't automatically take fixed position objects into account and should be defined manually. We also currently use generic data provided by moving companies to estimate a weight of an object given its type. However, objects from a same type may have various weights, and therefore it would be important to integrate correct values to achieve more accurate results. And finally, our future steps. We definitely want to perform more extensive user studies. We also hope we can develop this tool for cross-platform AR/VR interfaces and also use more robust floor planning methods for the furniture manipulation. And with that, I guess that's it. Thanks very much for listening, and please feel free to share any questions. Thank you.
Mohammed, thank you so much for the presentation. Very, very interesting. I want to remind the audience to go to slide.do, Slido, IEEE VR 2020 hashtag for any questions, session 11, which is collaboration. So just to remind, I wanted to, this is very nice work, the way you're mapping the different areas. And you did touch just a little bit in terms of what's next, but I was wondering if you could share some insight of what either you as a team or all the people could improve on this in the next steps, and maybe things that you said I could have done this better, or this was great, but I need to move to the next step now.
Yeah, sure. So I think one of the main issues is to conduct extensive user studies, and that would be really useful for us to understand what interactions are important for this kind of furniture rearrangement and manipulation. I guess we're also going to be working a bit more on examining different optimization methods. We did use evolutionary solvers, but I think we can also integrate other robust techniques in this regard. And in addition, adding the semantic segmentation module would also improve the workflow, have an end-to-end system. That's currently not our contribution, the semantic segmentation part, but I think it would be a very interesting add-on to this work.
Thank you. So we actually did get quite a few questions from the audience.
Okay.
Interesting. In a practical scenario, how will you perform the semantic segmentation?
Yeah, so that's a very good question. I think right now we do have maybe a lot of work in the field of computer vision that is working to have semantic segmentation from monocular videos or 3D point clouds. Again, it depends on what headset we're using, what sensors it has, and based on that, we're trying to integrate the semantic segmentations from those work. I think that's the general use case, depending on the headset.
Right, and your presentation is getting a lot of questions. I'm not going to be able to get to all of them. I do suggest the author may want to go and look at them, but so one question coming from Joan Lee is, great work. What aspect do you plan to evaluate in the user study?
Yeah, I think because this work requires the person to move furniture, to move the spaces around it, I think it would be really interesting to experiment what kind of interaction methodology would be useful. And again, another thing that we definitely want to measure is right now we're claiming that because people don't know of each other's spaces, it's going to be hard to communicate with each other and calibrate the space. I think it's really important to test this. So, having people to say, okay, do it by yourself and then do it with our system, how that works and what factors we're seeing improvement.
Right, and if you can keep the answer short, I'm going to try to get it to a couple more.
Sure.
If there were collisions between telepresence and walls, would it not be possible to expand the room with a digital room overlay?
That's an interesting idea. I mean, I come from an architecture background. Having the space, the real workspace at itself is also a very high priority. But again, there's a lot of techniques, especially maybe in redirected walking, that have explored this kind of manipulation of the virtual world itself.
Okay, and this is, I think, the last one that I'm going to be able to ask. Do you see this being possible with scans provided by AR headsets, or will people need to do a separate 3D scan of the room first?
Absolutely. We actually think we can use cloud systems for this. I mean, when the person initially scans this room is going to have it for forever. You know, maybe a few furniture is going to change. So the semantic segmentation won't be a problematic part. Whichever version they scan with is going to be used for general telepresence
Right.
communications for the system.
And I'm gonna ask the person moderating Slide DO to leave the questions for a little bit. Maybe the author wants to see it. There were some interesting questions. We won't be able to take all the questions online, but it was a great presentation. Thank you so
Awesome.
much.
Thank you very much for coordinating this
Yes.
and having everything online.
Yeah, Brooke, please tell Kyle that we need a sound effect. So, all right, great. So our next paper is titled Design and Initial Evaluation of a VR-based Immersive and Interactive Architectural Design Discussion System. And this is being presented by Ting-Wei Su, goes by Park. So that will be our next paper. And remind everybody to go to Slide.io, post the questions. You don't have to wait until the paper's over. If you have a question, just post it. And you can vote on the best questions. So Mohammed, thank you so much, and we'll go to the next paper. Again, the next paper is Design and Initial Evaluation of VR-based Immersive and Interactive Architectural Design Discussion System. Thank you.
This paper
because
presents the
it's
design and
almost
initial
serves
evaluation of a
Shiokagi Taiwan.
VR-based architectural design discussion system.
Yeah.
In this system, participants, including teachers and students, can discuss and modify or create the object in real time, sharing their ideas with voice and sketching, and roll back to previous state of discussion to make some changes or to start a new direction of discussion. An initial study shows that the feedback for participants were positive and suggested that the system could be effective and useful for supporting architectural design discussion. In traditional architectural education, design discussion is an important course. In a traditional design discussion course, the designer presents the design solution with 2D drawings and a physical mockup, and then the teacher coordinates the discussion, review, and feedback. The discussion proceeds by using voice and sketching on paper or whiteboard. There are some issues of traditional design discussion. First, all the participants should meet in the same place and at the same time. Second, with 2D drawings and physical mockup as discussion medium, participants cannot visualize and navigate from inside, and a lot of additional mental effort is usually required to imagine what the model looks like from the inside. Also, participants have to pay more mental effort in associating the object represented by 2D sketching on papers with the 3D scene. Last but not least, the physical mockup cannot be modified during discussion, and it is difficult or challenging to roll back to a previous state of discussion to make some changes or to start a new direction. In this paper, we proposed a VR architectural design discussion system aimed to resolve the aforementioned issues in the traditional design discussion. First, with virtual reality, participants can join in the same virtual environment even they physically stay in different places. During discussion, participants can navigate the architectural model at human scale from the inside out, and manipulate the models during discussion, express their ideas via sketching in 3D space or on object surface, and roll back to previous visited place or previous state of discussion. The system also provides several support tools for discussion to enhance the feeling of presence in virtual reality. Here's a small video clip of our system to illustrate the design discussion scenarios. 3 students and 1 teacher are discussing how to modify a platform of the model, and the platform is manipulated during the discussion. This clip is built from the teacher. We use Unity to build the platform of our system. The first Open Unity client will treat as host, and all other clients will connect to host server. When a user modifies models by adjusting the parameters, the host is responsible for transmitting the modified data to RhinoCommon through the socket. Then RhinoCommon updates the value to RCP, and Grace Hopper regenerates the mesh data and directly transmit it back to the host, also via a socket. The host will again synchronize the result to other client. When a user modifies the model without adjusting the parameters, this operation will transmit to server and synchronize in both server and client. Let's talk about the functionalities provided in our system. First, we provide a personal space widget to do rotation, translation, and scrolling, and to create new primitive objects in virtual environment. Second, mid-air and on-surface sketching are provided for participants to express their design ideas. Some other tools such as Minimap, Gather-All, and Bookmark also proposed to support the discussion. Finally, an intuitive rollback mechanism is used to guide the user back to a previous state of discussion. Object manipulation using raycasting or virtual hand are intuitive and natural, but are still under some constraint. For example, raycasting can support only radial movement for translation. Moreover, this method also generally suffers from a lack of precision. Hence, we propose a hybrid method that combines raycasting for object selection and object manipulation through widget, to provide more accurate operations and allow more complete transformations. First, we select object using raycasting. Then we choose type of transformation shown on the main menu. A widget will appear in front of the user, and user can select axis for the transformation. After axis selection, user drags a bit, which a small cube placed in the center of the widget to perform object manipulation. While doing the transformation on the widget, the amount of translation distance, rotation angle, or scale factor also shows in the widget, and the select object in the workspace is transformed accordingly. To further facilitate this discussion, in addition to create of new object, we also provide mid-air sketching and on-surface sketching. With mid-air sketching, we can sketch a rough wireframe for a rather complex object to express the design idea intuitively. On-surface sketching is used to draw on object surface, such as walls or grounds. Here's a demo video of mid-air sketching. The teacher draws a wireframe representing an object in room space and tells the student where the pose should be added. In traditional design discussion scenarios, participants are usually positioned in a nearby area. In virtual environment, it's quite often that the participants may stay far away from each other. Moreover, navigating in virtual environment in full scope can create a sense of immersion, but may lead to loss of spatial awareness of the architectural model. To reduce the problems, we provide a minimap, which is a top view of the building floor augmented with information about participants, such as their surnames, the roles, the positions, and orientations. Minimap could help to enhance the spatial awareness of the virtual building and the understanding of the presence of others. Minimap can also provide an easy way to do teleportation. Participants can directly teleport to any place in the virtual environment by touching a position on the minimap. In this system, we also provide a Gather-All functionality. As just mentioned, in virtual environment, it's quite often that the participants may stay far away from each other. When teachers like to express ideas, he or she may expect to have students gather around. Once Gather-All function is executed, students are automatically teleported to a location close to a teacher and then adjust according to their head direction, such that the teacher stays in front of them. In traditional classroom or seminar scenarios, participants usually take notes about important content or information. However, note-taking in virtual environments cannot be easily supported. Instead, we provide a bookmark functionality to mark a time point for specific state of architectural modeling, corresponding to an important design modification or dialogue. When a bookmark is issued, we store the state of the architectural model as well as the position and orientation of the participant who issued this comment. The bookmark information will be used as a guidance for the rollback functionality, or for the course reviewing that uses the playback of the achieved design discussion content. During the discussion, participants usually have a certain level of memory about what happened in the past. When a participant wants to roll back, we guide him or her to find a region of interest by offering a 2D minimap augmented with information about where the actions and bookmarks were made. On the minimap, actions such as object modification or creation are marked by flags, and bookmarks made by participants are marked with yellow stars. In addition to flags and stars, a dashed line representing the participant's path is also shown on the minimap, which reminds the participant which region he or she went through and implicitly put the actions and bookmarks in the time sequence. Since participants usually have clear memory about where the action happened and when they happened, to support rollback to a specific time point, we first revert to a specific region and then select an object that was modified or created in the region to confirm the desired time point. The objects that were modified or created are rendered and highlighted at the positions after modification with color coding for the order in time. Here shows the demo video of rollback. First, user editing the statue, translate and scale it. Then he moved to other place, trying to build an ifs and posts. After a long editing of ifs, he may want to back to the time point that the posts are not even being added. So he opened the rollback mechanism, clicking a flag to back to a specific region, and choose the top of the statue. Different position of both shows the different brightness, and after he selects one of them, the environment back to previous time, and the posts of the ifs have not been added. Now the user can move to different direction of design discussion. It is difficult or challenging to conduct a user study that compares our system against with a traditional architectural design discussion. Instead, we conduct an initial evaluation to evaluate the system with architectural major students who have already received traditional architectural design discussion experience in real classroom. Therefore, based on their experience, the architectural teachers and students were capable to evaluating the usability and user experience and effectiveness of our system against their prior experience of the traditional architectural design education. Our initial user study question was, to what extent is our system usable, useful, and effective to use in remote architectural design discussion? We divide the participants into 4 groups. In each group, one designer brings his model to a course, and the teacher starts to discuss about the building. He may first navigate the building, editing, and brainstorming to help students understand how to improve his work. There were 5 questionnaires to assessing the user experience, impression, and effectiveness of our system, including simulator sickness, presence and co-presence, cognitive and physical workload, system usability, and system evaluation questionnaire. In applied and research constructs with complex VR applications, it has now become standard practice to measure these constraints that we have totally measured in our system. We believe that it sheds light on different aspects of the user experience and were highly relevant to the simulation experience of VR architectural design discussion. Fortunately, all the participants did not give up after a few questions and stay focused in the post-experience questionnaires around 30 minutes. In the simulator sickness questionnaires, the difference in score, which indicates sickness caused by experiencing design discussion in virtual reality, was not significant. In presence and co-presence questionnaire, users usually have feelings or being present in the virtual design discussion during their experiment. About the question 12, the virtual world seems more realistic than the real world, as a lower grade. It is reasonable, since the model in virtual environment is a plain model without realistic texture and lighting. NASA TLS questionnaire measures the effort in the system. The result shows that mental demand, physical demand, and effort has relatively high score. The high mental demand score shows participants were engaged in a discussion. The high physical demand may be due to the hardware problems, such as head-mounted display. The high effort means the user feels that he spent more energy to achieve their level of performance. With linear regression, we observe that for a unit time period, the effort required for object transformation is much greater than for sketching. Most of the scores in IBM System Usability Score questionnaire get high. The extremely low score happened in question 6. It was easy to learn to use this system, which means only 20 minutes is not enough for user to learn how to use the system. More time for training may be necessary. In question 9 and 18, some users think we do not provide enough error messages, and some functionality seems to be expected but not available, for example, copy and paste. Our comprehensive system evaluation questionnaire that we designed consisted of 2 parts of evaluating our system's functionality, which is overall system evaluation and system interactive functionality. In overall system evaluation, all the questionnaires get high score, which means users usually agree that our system is interactive, enjoyable, and useful. While considering each functionalities, we found that all functionalities get high score, and translation performs better score than rotation and scaling. We guess that's because we only provide object information in both personal and object space. This may imply that providing object modification in both object and personal space is a better model to facilitate growth to find changes. Most of the participants like the present VR architectural design discussion system. They think the system is easy to use and provide an effective way to share their designs. More than half of the participants' comment on min-map functionality were positive. One participant said, "I can quickly know the structure of the building. It also helps the user to locate others during discussion." Some participants are suggesting that we should allow users to adjust the scale of the 2D min-map because they want to see more details of the building. Most of the participants like the interface of object modification present in our system. One participant said, "I can move objects precisely with translation in personal space. It's convenient to me." Many participants like the sketching functionality. The sketching is also helpful to facilitate the architectural design discussion. Since the rollback functionality can be applied by the instructor only, we have feedback from 2 instructors who used the rollback interface during the discussion. Their responses are positive. In the meanwhile, some participants point out several drawbacks and limitations of the present system. Some drawback comes from hardware limitation, such as head-mounted display. Some participants mentioned that they could not tell if they touched the interface or not. Additionally, the process of object manipulating can be improved, such as snapping. And others want to add some more functionalities, such as object copy and paste. As a concluding remark, we present the design, implementation, and initial evaluation of a VR architectural design discussion system. The expected goals were that the participants can have not only much better spatial understanding about the architectural model, but also more effective and efficient design discussion experience. The result of our initial user study indicated that the aforementioned goals have been reasonably achieved, and that some functionality provided in the system are helpful for architectural design discussion and learning.
Thank you so much for your presentation. We are running a little bit. We are running a little bit late, so I'm going to try to keep it as short as possible. Remind people to use Slido. So far, I don't see any questions from the audience that may be coming in, so I'm going to go ahead and ask you a question. So you were conducting the study, and I think it's really interesting to understand how users were perceiving this in a subjective matter. What do you see as the limitation of your study? What are the limitations?
Currently, the limitation is because we use the model built from the student, from the user. So actually, we haven't yet find how to transmit the texture coordinate into the Unity. So you see all the models are plain and without beautiful texture, beautiful and realistic texture. And right. Yeah.
Okay, yeah. No, I was talking more about external versus internal validity and the fact that, but yeah, that's also a good comment. I'm gonna thank you again. Thank you so much for the presentation.
Yeah. Thanks.
Because we're running a little bit late, we're gonna move to the last presenter. It's an uninvited paper from IEEE TVCG, Transaction Visualization and Computer Graphics. So was the first paper, which is not invited, but was accepted by the Transaction Visualization and Computer Graphic Journal from the IEEE. This last paper is called Multi-Window 3D Interaction for Collaborative Virtual Reality. It's going to be presented by Andre Kernert. Remind, again, please ask your questions early in Slido session 11. And when this session is over, please go to Hubs and enjoy Hubs, whether you're using a headset or the desktop. Thank you, Andre, for being here. You're the last presenter. And thank you so much.
Hello everybody, my name is Andre Kunert and I welcome you to my talk on multi-window 3D interaction. The main focus of our research at Bauhaus University Weimar are collaborative workplaces based on multi-user projection technology. 3D tracked shutter glasses separate the time sequential images on the display such that each user perceives the scene from their individual viewpoint. This creates a shared 3D workspace that facilitates joint exploration and gestural communication about the 3D data. The whole group can be navigated through large-scale virtual scenes using a stationary steering device, which we call the Spheron. We extended this setup with a multi-user 3D tabletop. While the wall display facilitates egocentric exploration, the tabletop rather affords top-down miniature views. The tabletop view can be adjusted freely using multi-touch gestures. Both displays serve as independent viewports into the same virtual scene. Virtual viewing windows provide even further views into the scene. We attach them to a tracked handle, which allows us to move them continuously between the two physical displays. The virtual views can be adjusted freely and enable section views of the models. Their viewpoint can also be seamlessly applied to the main displays, for instance as a shortcut for long-distance navigation. 3D interaction tools such as Array Pointer are operable in all views and can be easily moved between the displays to interact with objects from alternative viewpoints or with objects at different locations in the scene. The tight integration of multiple co-located but independent displays into a joint workspace creates novel interaction possibilities in the form of specialized views, focus and context visualizations, and opportunities for direct comparison and data exchange. A further very important aspect is that such workspaces can facilitate and structure cooperative work. Previous research showed that collaborative workspaces in general benefit from the inherent support of tightly and loosely coupled cooperation phases. Tight couplings imply direct cooperation and frequent communication between the users. In more loose couplings, the users follow the same global objective, but predominantly focus on individual subtasks and have less direct exchange. User interfaces for cooperation should comply with these different requirements and enable fluent transitions between these phases. Another important aspect of collaborative workspaces is the spatial behavioral pattern of territoriality. Stacy Scott and colleagues observed the emergence of dedicated group, storage and personal interaction territories in real-world settings. This subdivision can help to minimize interferences and increase coordination between the collaborating users. A main goal in the design of our multi-window workspace and the corresponding interaction techniques was to comply with such requirements for collaboration. Each of the separate display areas forms their own viewing and interaction territory that can be used privately for preparations in individual work or can be used publicly for sharing one's insight and findings. Our workspace implicitly supports tightly and loosely coupled cooperation, since people can easily form subgroups at the displays or split off from others by changing over to a separate display. While we believe that our workspace enriches cooperation and creates novel interaction possibilities, there are several challenges and particularities in its realization, which I want to explain now. As a first step, we have to realize the individual viewing capabilities per display. Here exemplarily is illustrated for the tabletop and the wall view. To the left, we see the physical workspace with both displays and two users. On the right side, we see a top-down miniature view of the virtual scene. Now the wall display, which shows an egocentric view of the scene, is highlighted in red. On the right side, we see the corresponding screen and viewing positions of the two users in the scene space. For better visibility, the color to the right shows a magnification of this location. Now the tabletop is highlighted in green and shown at the respective location in the scene. Since a miniature view is shown on the tabletop, the screen and the users are represented larger in the scene space. Nevertheless, the spatial configuration of the tabletop and the users matches the real-world situation. Note that the users are now represented twice, with separate viewing setups at two different locations in the same scene. Let us now have a look on the 3D Array Pointer, highlighted in yellow, aiming across both displays. In order to be operable in both display contexts, the pointer needs to be represented at both viewing locations as well. Once at the wall view location visible in the white callout, and a second time at the miniature view location of the tabletop. Thus, two equivalent pointer representations exist in parallel. Potentially, they can induce actions at different locations in the scene with different or even the same objects at the same time. For direct 3D interactions such as object dragging, this ambiguity must be resolved. Here the device input needs to be associated with a single spatial context. Input disambiguation is also known from other interaction domains, such as 2D desktop environments where the solution is straightforward. In case the input cursor is situated above multiple application windows, the topmost one is selected as the interaction focus. In 3D environments, the disambiguation cannot be solved in 2D image space anymore. Sturff and Smalstieg presented through the lens techniques, where the lens provides a secondary viewpoint into the scene. Using a tracked stylus, their system provides manipulation capabilities within the main and the secondary view. If the tip of the stylus lies inside the viewing frustum defined by the lens, the manipulation is executed within. If the stylus is outside of this volume, the interaction scope falls into the main view. In immersive 3D virtual environments, the viewpoint of the user is constantly updated by head tracking input. Thus, the relationship between the tracked input device and the visible scene section is highly dynamic. Slight positional changes of the user or the input device might result in a different anticipated interaction context. In multi-user virtual reality, there's another level of complexity involved, since the relation between input and content may vary severely between users due to their different viewpoints, and may thus also alter their expectations regarding the interaction. To realize continuous interaction capabilities across disjunct viewing windows, we propose a context selection pipeline based on the visibility of the potential interaction windows, the tools and their effects for the operating user. This pipeline is now shown for the exemplary situation on the right side. The tabletop and the wall display show different sections of the virtual scene highlighted in their respective color. The operated pointer could potentially interact with both sections. In the first step, the visibility of the two viewing windows is checked. Windows that are not visible to the operator are not considered further. This is not an issue here, both are visible. Then the ray is checked for any intersection with both viewing frusta, as is the case here. Note that the physical handle can be outside these frusta. It only matters if at least some sections of the ray fall into the viewing volume. In the next step, both ray representations are checked for intersections with geometry at the different locations in the scene that are defined by the two viewing windows. Both representations intersect with scene objects, but here only the intersection point of the wall ray is visible to the user. The intersection of the tabletop ray, shown in green, is outside the green tabletop frustum. The object dragging is thus executed with the tree at the wall display. This was a straightforward case so far. Now in a second example, I've changed the situation a bit, since the ray pointer is now held a bit lower by the user. Up to step 4, the disambiguation process is the same as before. But now in the effect validation step, we still have the issue that we cannot select a single interaction context, since both intersection points are visible. Thus, we have to make the decision in the final step, where the intersection points are prioritized regarding their distance to the tracked input handle. As such, the tabletop context is chosen for interaction as it is the closer one. While the decision sequence for a ray seems rather obvious, it is designed for other tools as well. We generalized the representation procedure and the context selection heuristics into a high-level software design, which we call multi-context tools. Its components can be configured and adjusted to varying needs. For further details, please refer to the paper. We use this software structure to realize a variety of different 3D interaction tools. The flashlight tool shown here can have multiple active representations at the same time in different views, because we want the lighting effect to appear continuously for the user. Our handheld virtual viewing windows are particularly interesting, since they provide an own interaction context for other tools to operate in, and secondly, they are also presented themselves in both physical displays in order to appear continuously. We also applied the multi-context structure to objects, such as they appear uncropped in adjacent viewing windows during drag-and-drop transitions. We conducted a formal user study to identify the general benefits of multi-window 3D interaction, which we attribute to the possibility of more subtask parallelization while remaining in close exchange among each other. We set up a within-subject study design with a multi-display condition featuring the wall and the tabletop, and a single display condition utilizing only the wall display. We also designed a collaborative visual search task, where predefined views at handheld windows had to be found in a virtual city model and placed at the assumed capturing position. 10 images could be found within a 20 minutes time limit in each condition. During the task, the participants could freely decide when and where to join or separate their efforts. For instance, they could search in parallel for target perspectives at the separate displays, or distribute responsibilities where one user is searching and the other one is already preparing the final alignment of a located image. At least during the final alignment phase of the images, the task involved a tight coupling between participants with joint decision-making. The located perspectives had to be aligned as precisely as possible, and they had to be approved by both users. Now coming to the results. On average, the number of successfully solved tasks is 8.2 for the multi-display condition and 7.4 for the single display condition. This indicates that the users could exploit the expected benefits of our multi-window environment to different degrees. This diagram shows the overall and the joint usage of both displays by users in the multi-display condition. The wall is almost continuously used over the course of the task, and about 50% of that time by both users. The tabletop is used only for half of the time on average, and hardly at all by both users simultaneously. For an in-depth analysis of the applied strategies and cooperative patterns, we recorded the users' positions and their activities throughout the task. The colored bars above and below the black timeline visualize both users' presence at the different displays. The red vertical line indicates completed tasks. This recording shows a cooperation strategy with a high level of parallelization when working with both displays. Both users stay and work in parallel at the different displays for most of the time. The user depicted in blue only briefly joins the partner at the wall display for the final image alignment phase of each subtask. You can see these transitions if you focus on the immediate time range around each red vertical line. This strategy of task distribution results in a high performance rate of this group in the multi-display condition, where all 10 images were found in only 16 minutes. In the paper, a more detailed version of these diagrams can be found that give further details at which of the displays the users carried out their activities over the experiment. To sum up the contributions of our work, we presented a novel collaborative multi-window 3D workspace that supports diverse types of cooperation and also offers novel interaction possibilities. Its design and implementation included the challenge to realize seamless 3D interaction across independent but co-located 3D displays. We proposed a high-level software design for multi-context tools and described its application for a variety of tools and interaction objects. Finally, we conducted a user study that demonstrated general benefits of multi-window 3D interaction in terms of user preference, comfort, and task performance. As future work, we will continue the analysis of working strategies and cooperative patterns in multi-user VR systems. We will also refine and develop new interaction tools for particular use cases, such as the inspection and monitoring of built infrastructure based on high-quality 3D scans. And with this vision, I'd like to conclude my talk. Thank you very much.
Thank you, Andre, for your presentation. Thank you so much.
Thanks.
So we're going to see questions from the audience first to see if we have any questions. Remind everyone after this, there will be a break at, and the next one will resume at 3:30, the next session. Why do you think, this is a question from the audience, why do you think tabletop is not used jointly by the users as much? Would this be different if it was mounted on the wall or if it was a bigger display?
I don't think so that this relates to the size of the tabletop itself, but rather to the tasks that can be executed efficiently at the tabletop. And I hope this gets through that for large periods of the time, the users could separate at both displays, working on the tabletop and on the wall display in parallel. And basically, they searched for the target perspectives simultaneously, and therefore the tabletop was very well suited. But there was also the phase where the users had to join their efforts and place these figures at the exact capturing position. And this can best be done at a large screen where an egocentric view was shown, and there where also a one-to-one scale view was shown, where the user could adjust the one-to-one view. Therefore, these phases where the joint decision-making and the exchange are required are more easy to do at the wall display, and that might be the reason that the tabletop was not used in parallel so much.
Well, thank you so much. Because we have run out of time already, we're going to cut this short. First, I do want to thank all the presenters for being here, answering questions. So thank you so much. We're gonna. I do want to ask my producer, Brooke Bowers, on the back. He's behind the screens, helping me along the way. And again, my name is Francisco Ortega from Colorado State. Thank you for watching this session. I want to thank everyone organizing the conference for doing a great job and for inviting me to chair this session. And with this, I'll sign off and make sure to go to Mozilla Hubs for some fun. Thank you.